Hi students, welcome back to the new session. In this session also, we are going to discuss about rules pertaining to concept of electronic configuration. In the previous video, we discussed about Arbo principle. Now in this video, we are going to discuss about another rule related to electronic configuration, that is Hund's rule. Hund's rule. Hund's rule was proposed by Friedrich Hund. Okay, so this Hund's rule is proposed by Friedrich Hund. Proposed this Hund's rule. According to Hund's rule, pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. I will write the statement on the board. Okay, now the statement is pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. Okay, so pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. Now, this is a statement related to Hund's rule. In some books, it may be given as follows: whenever degenerate orbitals are available, pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. The statement you can write like this also: whenever degenerate orbitals are available, pairing of electrons takes place after all the available degenerate orbitals are occupied by one electron each. Sir, we unable to understand what is the meaning of degenerate orbitals. I hope so. In the previous video, I explained about it. But for your sake, I am going to explain again for better understanding purpose. So, what is the meaning of degenerate orbitals? Okay, the orbitals having same energy. What is the meaning of degenerate orbitals? Okay, means the orbitals having same energy. The orbitals having the same energy are called degenerate orbitals. For example, sir, can you please give an example to understand this? What is the meaning of degenerate orbitals? As you know well, we have primarily in 10th level we are going to discuss about we had a discussion about only three orbitals primarily, that is s orbital, p orbital, d orbital. You know well, s orbital contains maximum 2 electrons, p orbital maximum 6 electrons, d orbital maximum 10 electrons. Whereas in s orbital, we know s orbital is having a spherical shape, spherical or circular in shape, and p orbital is a dumbbell, and d orbital is a double dumbbell shape. Okay, so in s orbital 2 electrons are there, in p orbital 6 are there, in d orbital 10 electrons are there. Where s orbital does not have any suborbitals, there is no sx, sy, sz or some other way. Okay, s orbital does not have any degenerate orbitals, so only one type of orbital. If s orbital is in first shell, it is 1s, second shell means 2s, third shell means 3s, 4s, and so on. I told you already, I explained in the previous class. Whereas p orbital is having three types of suborbitals. They are px, py, and pz. Understood? They are px, py, and pz. All the degenerate orbitals of this p, all these suborbitals of the p are having the same energy. For your understanding purpose, even I will draw the diagram related to this p orbital. So, in p we are having three degenerate orbitals. This is x-axis, this is y-axis, and this is a z-axis. If the dumbbell shape falls on x-axis, this is called px. Okay, and now this is what py. This is y-axis, this is a py orbital, this is x-axis. As usual, this is z-axis. And next one is we are having a pz orbital. This is x, this is y, this is z. This is a z-axis, this is called pz orbital. So this p orbital has got three degenerate orbitals. All these degenerate orbitals of p all are having the same energy. Okay, this is px, py, pz. You know well, the p orbital starts from second shell. If it is starting from second shell, it is called, I can write this one as 2px, okay, 2py and 2pz. Understood? A total of p orbital maximum contains 6 electrons are there. Each p suborbital is having 2 electrons equally shared here. Here 2 electrons, 2 electrons, 2 electrons. Each p orbital, okay, each p suborbital of p is having 2 electrons each. So totally p has got 3 degenerate orbitals. All the degenerate orbitals of p is having the same energy. I hope you understood. So what are degenerate orbitals? The orbitals having same energy are called as degenerate orbitals. Whereas if you go in terms of d orbital is having a shape is a double dumbbell, and d orbital maximum number of electrons is how many? 10 electrons. And d orbital has got 5 suborbitals. In d orbital, if you go to the d orbital is having a double dumbbell shape. Okay, double dumbbell shape. Understood? And it is having a maximum of 10 electrons are there. Okay, and d orbital has got 5 degenerate orbitals. They are dxy, dyz, dzx, dx square minus y square, dz square. Understood? Now we can draw all the shapes, no problem. Okay, I can draw. Now these 5 orbitals of d are degenerate orbitals. Every orbital is having same amount of energy. Listen carefully. Now we have dxy. Now this is a x and this is y. One dumbbell, this is another double dumbbell shape. I told you already. D orbital is having double dumbbell shape. dxy, d. If I make it this one as a y, okay, and dxy, dyz. Otherwise, you can write, okay, this is a dxy, and if I make it this is y and this is a z. Now one dumbbell is like this, another dumbbell is like this. This is called dyz. Okay, next one is dzx. This is z-axis and this is x-axis. One dumbbell is like this, another dumbbell is like this. So this is a dxy, dyz, dzx. And next one is we are having a dx square minus y square. Now this is x-axis, this is y-axis. Here one dumbbell and here is another dumbbell. Okay, this is what dx square minus y square. And next another type of d orbitals we have is, I will draw that one here, okay, because of space issue, and I am going to draw that dz orbital here. So this is a z-axis. If you consider this one as z-axis, otherwise you can consider this one as z-axis. Consider, I told you to consider like z-axis, then one dumbbell will be here, another dumbbell, okay, gives rise, this is a dz square. This is generally called as a torus. Okay, so each suborbital of d is having 2 electrons. Is having a 2, here is 2, here is 2, here is 2, here is 2. 5 2 is a total of how many electrons? 5 2 is a 10 electrons. I told you already, d orbital is having maximum 10 electrons. D is having a 5 suborbitals. They are dxy, dyz, dzx, dx square minus y square and dz square. I hope you understood this. Okay. So this is y-axis, and here listen carefully, dz square, 5 suborbitals are there. All these suborbitals are called degenerate orbitals of d is having the same amount of energy. I hope you all understood what are degenerate orbitals and how many degenerate orbitals are present in p orbital, how many degenerate orbitals are there for d orbital, how many degenerate orbitals are there for s orbital. There are no degenerate orbitals. Only one type of orbital is there in S. Okay, there is no suborbitals of S. Okay, I hope you understood the statement, and even I explained clearly about degenerate orbitals related to p orbital and okay, d orbital. Now I will go with a small example for ease understanding purpose. I will go with an example of I will start from the element like boron. Okay, I will go to several examples: boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, boron atomic number is 5. Boron atomic number is 5. Carbon is 6. Nitrogen is 7. Oxygen is 8. Fluorine is 9. Neon is 10. Okay. Now, boron. Boron atomic number is 5. It contains 5 electrons, 6 electrons for carbon, 7 electrons for nitrogen, 8 electrons for oxygen, 9 electrons for fluorine, 10 electrons for neon. Now, sir, how these electrons are filled in degenerate orbitals, that we have to understand, because we know the basic way to write the electronic configuration. Okay. Now, I will write directly like this: 1s2, 2s2, 2p1. Okay, 5 electrons are there. 1s2, 2 electrons, 2s2, 2 electrons, 2 plus 2, 4 electrons, plus 1, 5 electrons are there. Now, if I write very clearly to represent the electrons in the suborbitals, the degenerate orbitals of p, now I will write this, here it is, for example, and this is 1s2, this is 1s2, and here 1 electron, okay, anti-parallel spins. So, next one is 2s2. Here is 1 electron, 1 electron. Next, go with the p orbital. I wrote directly for 1s2 and 2s2 directly because s does not. I wrote directly for s orbital as 1s2, 2 electrons, 2s2, 2 electrons. But why I wrote like this directly? Because s does not have any degenerate orbitals, whereas p is having degenerate orbitals. Now in p we are having okay, 3 suborbitals are there. That is 2px, 2py and 2pz or z. So one electron is there, that electron will be first filled here. Understood? Now we'll go to the next example of carbon. Carbon has got atomic number 6, configuration is 1s2, 2s2, 2p2. Okay. Now I will write this. Here it is 1s2, 2 electrons, and here is a 2s2, 2 electrons is there. And in case of this one, 2px1, 2py0, 2pz0. Okay. Now we have 2 electrons are filled, 2 filled, 4 is completed. Now go with the 2p2, 2 electrons are there. First, this is a 2px, this is 2py, and this is a 2pz. Na? So in 2 electrons, first one electron will be filled in 2px, another electron cannot be filled directly in 2px. Okay. Pairing, I told you the definition statement. Pairing of electrons takes place after all available degenerate orbitals are occupied by 1 electron each. So first one electron will be singly occupied. So out of 2 electrons, 1 will be filled here, remaining 1 will be here. There is 2py1, 1 electron. Now if I go with the nitrogen, atomic number is 7, 7 electrons are there. 1s2, 2s2, 2p3. Now in this, as usual, 1s2 will be filled directly. Now go with the 2s2. We have 2 electrons, and 2p3 we have 3 electrons now. So I am going to show the degenerate orbital. This is 2px, okay, 2py, 2pz. Here it is 0 already. Now 3 electrons there, first 1 will be filled. Understood? You can't fill directly as like this. 2px2, 2 electrons, 2py, 1 electron like this. It is totally wrong. Understood? So according to the statement, pairing of electrons takes place after all available degenerate orbitals are occupied by 1 electron each. So 1 will be filled. First 1 will be filled here. Okay. And another one will be here. And third one will be 2pz1. It is here. I hope you understood this. Okay. So degenerate orbitals 3 are there. Okay. 2px, 2py, 2pz. 3 electrons. 1 will be filled here. 1 will be filled here. 1 will be filled here. I hope you understood this. Next, if I go with the oxygen, whose atomic number is 8, configuration is 1s2, 2s2, 2p4. Now this is a 1s2, 2 electrons, and here it is a 2s2, 2 electrons, and in p orbital we are having a 2px, 2py, 2pz. Okay, out of 4 electrons, first 1 will be filled here, and 1 will be here, 1 singly occupied, 1. then only pairs. Out of 4 you got 1, 1, 1. 2px1, 2py1, 2pz1. Now one more is there that I have to fill in 2px only. Then it will become 2px2, 2py1, 2pz1. First 1 electron, then only the pairs. Okay, you cannot write directly the pairs 2px2, 2py2, 2pz0. You should not write, because according to Hund's rule, pairing of electrons takes place after all available degenerate orbitals are occupied by 1 electron each. First 1, then only the pairs. I hope you all are understanding. Next, go with the fluorine, whose atomic number is 9, same as usual. Okay, this is 1s2, 2 electrons, and here it is 2s2, 4 electrons are filled. So configuration, if I write 9 electrons, configuration is 1s2, 2s2, 2p5. These 5 electrons, out of these 5 electrons, initially this is a what 2px, 2py, 2pz, 5 electrons. First 1, 1, 1. Out of 5 you got 3. The remaining 2 will be form the pairs 2px2, 2py2, 2pz1. I hope you all are understanding this. Okay. And next you can go with the neon. In the same passion, go with the neon. Neon atomic number is 10. It contains 10 electrons. Configuration is 1s2, 2s2, 2p6. This is neon. Atomic number is 10. 10 electrons are there. Configuration is this. Now, if I write orbital level clearly, 1s2, 2s2, 2 electrons, and in 2py, okay, 2p we are having a 2px, 2py, 2pz. 3 degenerate orbitals I am showing. 6 electrons are the total. How these electrons are filled, sir? First 1, 1, 1. Then only the pairs. Now we can write 2px2, 2py2, 2pz. Z2. And simple configuration we are writing as 1s2, 2s2, 2p6. It's over. Okay. I hope you all understood. Give one example even for that d orbital containing degenerate orbitals, how they are filled, sir. Okay. Now go the next higher case element. One example, go with the copper. Okay, we'll go with the copper for better understanding. Otherwise, you can go with the zinc also. I will go with the copper. Okay, now copper. Copper atomic number is 29. Its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, HL, 4s2, 3d, 9. But to make it stable, I explained in the previous class, I will write the configuration as 4s1, 3d, 10. Now here it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d, 10. Now how the orbitals are filled, sir, according to Hund's rule. Now we have, this is a 1s2, and here we are having a 2s2 and 2p6, 2 in 2p we are having a 3 degenerate orbitals, 2px, 2py, and even 2pz. Out of 6 electrons, first 1, 1, 1. Then only the pairs. Up to here, how many completed? 10 completed. Up to this task we completed. Next we are having this 3s2. Now this is a 3s2, 2 electrons, and in 3p also, in the same passion, 3px, 3py, 3pz. You have to write 2px2, 2px2, 2py2, 2pz2. Okay. Now here, out of 6 electrons, first 1, 1, 1. Then only the pairs. Okay. Next, after that, we have 4s1. I told you, okay, orbitals with half filled or fully filled electrons are stable. So I am making this, to make this fully filled, I am making this one as half filled. Now this is a 4s1, 1 electron. Next we are having a d orbital. We know that d has got 5 degenerate orbitals. They are, okay, 3dxy, 3dyz, 3dzx, okay, 3d x square minus y square, 3d z square. 10 electrons are there, na? So first 1, 1, 1, 1. Then only the pairs, because we are following the Hund's rule. Here is 3dx2, 3dxy2, 3dyz2, 3dzx2, 3dx square minus y square 2, 3dz square 2. Okay, I hope you understood this. This is the way we have to fill the electrons according to Hund's rule. This is the end of explanation related to Hund's rule. In the next video, we are going to discuss about Pauli's exclusion principle. Okay. So without understanding the concept of quantum numbers, you cannot understand the Pauli's exclusion principle. So hence, in the next video, I am going to explain about types of quantum numbers, and after that, I will explain about Pauli's exclusion principle. I hope you understood. Okay, the topic related to Hund's rule and even the previous videos also. Okay, if you are having any doubts, please comment in the comment section, like, share and subscribe. Thank you.